May the force be with you. Ounces of avocado today, a pound of guacamole tomorrow. Do this. Do not sorrow.
Okay, sorry. That was my Baby Yoda. I don't even know if Baby Yoda talks. I'm maybe like 2 episodes in on that one, and it kind of lost me, but maybe I'll go back to it. But Baby Yoda's pretty cute. Yeah, so tomorrow is May the 5th, or Cinco de Mayo, so don't forget to get some good Mexican food tomorrow. All right, so we're going to do chapter 20 today. Yeah, here's our schedule. I don't know why I still show it, but I still have tentative here, so I guess it's okay. We will have the exam 3, and it's not 18 and 19. Exam 3 is it's this Wednesday, not next Wednesday. And it's going to be over chapter 16 to 19. So as it says there, do lots of mechanisms. There'll be lots of mechanisms on it, as usual, and practice them, and everything else will get better. So just practice all your mechanisms. It'll really help you. It'll surprisingly help you a lot on the retros and other things. I filmed a couple of reactions in lab, and I'm going to share those results shortly, but I'll just be busy with the exam writing now. But then I won't hit you with a bunch of like time-consuming lab reports to do, but I want to give you some more lab experience, so you'll get those, and I'll make them fun, easy points for you. So keep turning in lab reports, the homework, corrections, etc. I've seen a little bit better results on that. It's good, keep it going, but maybe pause on it as of today when you watch this because you want to study for the exam. So my to-do list, so I got new labs preparations to do, the videos I got to put together, and I'll make a worksheets, data collection, etc. I got to write exam 3s and its keys, and I got to grade stuff a little bit. I got to do some paper airplane retro video. I'm waiting to do that. That won't take me too long once I get the last of the videos. And then your to-do list, study for exam 3, draw out mechanisms and more mechanisms, and do all the homeworks then after you've studied your notes and got your mechanisms down. Then try those grade chapter handouts. And some of the homeworks in the grade chapter handouts, I do have problems that involve reactions that we haven't gone over, that we skipped this year, and I've been phasing out over the years. And so if it looks totally unfamiliar, just ask me for help. I'll help you out with that. And then do lab reports, but maybe pause on those until you're done with exam 3. And then send in your epic paper airplanes. There's just a couple more left. I'm waiting to see those. I'm always excited when I get an email with someone's video, and then I'm going to throw them all together, and it truly will live up to its name. It's going to be epic. All right, so if you go to our mechanism quizzes area, this will help you study too. We've got the aldol condensation animation. So if you download that, animate it, and click through it and practice it, you probably already got it down already, hopefully, but it's good practice. And then the aldol condensation and Sir Robinson annulation cheat codes. If you haven't seen that, that's currently my favorite thing I've made this semester. So I hope you like that. Check that out. It'll be very helpful for you. So animate that. And then over here, I did add a new lecture PowerPoint. I made up one for chapter 20, which I'm going to go over, I think now. Yeah, let's do it. So I made this one up. It's got some of the main stuff from chapter 20. It's a good review. So first off, we're going to look at these electrophiles here. And we're going to rank them according to electronegativity and resonance effects, so induction and resonance. And it's pretty cool. We use these concepts, induction, resonance overall, to describe electrophilic aromatic substitutions, the chapter 15-16 stuff. We use it for acid-base chemistry, which we saw in chapter 16, and we're now been using it for electrophilicity, how much charge, positive charge you can get at these carbonyl carbons. So let's go through this. So the first one, the acid chloride. So we're looking at the chloride, we're focusing on that one. In terms of induction, is it more electronegative or less electronegative than hydrogen? It's more electronegative than hydrogen. So it'll be electron withdrawing relative to the hydrogen. What about resonance? Boom, electron donating, can donate in, right? So what wins, withdrawing through induction or resonance through donation through resonance? Overall, it's experimentally shown to be electron withdrawing. Why is that? Because the carbon's 2p atomic orbital doesn't overlap well with the chlorine's 3p atomic orbital. So the resonance is weak and the induction dominates. All right, now what about an anhydride? An anhydride is a really interesting one, and I want to make sure you understand this one. So we're looking at, like, say, just one side of it. So I'm considering this being the electrophilic carbon. It could be this side too, but let's just, well, I'm going to be looking that way each time. Okay, so overall, you say the oxygen is electron withdrawing compared to hydrogen, because oxygen's more electronegative than hydrogen. In terms of resonance, it can donate in, right? Boom, like that. So it's getting donation. So what is it overall? Stop and think about it for a second. I'm going to count you down. What is it? Is it overall donating or withdrawing? 5, 4, 3, 2, 1, 0. Wait a minute. Are most of you thinking, no way, that was overall donating an electrophilic aromatic substitution? Why would it be overall withdrawing here? This is a good story to this one. Here it is. So if you look at the anhydride, it has resonance like this, right? So it can resonate over to the left carbonyl, and it also resonates, boom, over to the right carbonyl. So a resonance hybrid can look like this. So what does that mean for either side of being attacked as an electrophile? Does that mean it gets as much resonance donation? No, resonance donation is only half to each side. So instead of getting like the full resonance donation to this side, it only gets half of it because half has to go this way. So that means it's weaker resonance to each side, and hence electron withdrawing induction beats out the donation in this case. Isn't that cool? So it turns out the acid chloride is a very strong electrophile. The anhydride's not as strong as the acid chloride, but pretty strong. It's just a little weaker. It's just like a milder acid chloride. All right, what about the aldehyde with an H here? Well, that one, it's the reference. So we don't say it's withdrawing or donating. It's the 0 point, just the reference all the way through. So we're saying chlorine is more electron withdrawing than a hydrogen. So it's more electrophilic than a hydrogen. All right, what about this? sp3 carbon here. It's electron donating because sp3 carbons, we consider it less electronegative than a hydrogen. Resonance, none. So overall, got to be electron donating. So if it's a donating overall, is it a weaker electrophile than the aldehyde? Yes, it's a weaker electrophile, a little bit weaker electrophile, the ketone versus the aldehyde. All right, now an acid and an ester, they're pretty much the same. So I'm just going to, oh, this is sp3 carbons, the detail for this one. The acid and the ester, they're pretty much the same. So I'm going to just kind of treat them together. Overall, they have oxygen, they're electron withdrawing. In terms of resonance, they are electron donating, and overall, what wins out? The electron donation. It's not like the anhydride. It's going to donate overall. So, and why is that? It's because it's got oxygen 2p to carbon 2p, strong resonance. So, does this make these carbonyls more or less reactive than the ketone and the aldehyde? Actually, well, these are both donating overall. I'm going to compare it just to the aldehyde first. So does it make it more reactive than the aldehyde? Yes, it's more reactive. No, it's less reactive, sorry, because it's donating in. It's less reactive. This carbon is not as positive as that carbon. Less reactive. All right, now what about the amide? Electron withdrawing, it's more electronegative than hydrogen. And then donation, electron donation through resonance. Overall, donating, just like the oxygen. And it's because of the 2p, nitrogen's 2p to carbon's 2p. Strong resonance. And actually, the nitrogen winds up even being a stronger donor than the oxygen. The reason, one way you can think of it, is that the nitrogen's a little less electronegative than oxygen. So this withdrawing is not as strong for nitrogen as it is for oxygen. And then in terms of these two, the oxygen actually winds up and the nitrogen are stronger donors than the sp3 carbon. And if you remember from the chapter 16 stuff, the electrophilic aromatic substitution, the sp3 carbons are weak electron donors, weak activators, whereas the oxygen and nitrogen are strong electron donors, so they're strong activators. Okay, so let's see this all put together. So what's the strongest electrophile in this group? Who is it? Which one is it? Yep, the acid chloride. The acid chloride is the strongest because the chlorine is overall withdrawing, and it withdraws a lot, making this carbonyl very positive. Who's second? The anhydride. It's like a mild acid chloride because its resonance is divided between the two, so it's a resonance domination is only half, so the induction withdrawing overrides resonance. Who's next? The aldehyde, because while these two groups are overall withdrawing, the aldehyde is the reference. It's like the 0 point. These are withdrawing, nothing. Who's next? The ketone, because the sp3 carbon is a donor relative to hydrogen, but it's a weak donor. Next up, the acid and the ester, they're pretty much the same, and they're both strongly donating. And then the amine, or not the amine, but the amide is the strongest donor because it is less electronegative than the oxygen, so it doesn't have as much electron withdrawing due to induction. And then, so what does that mean? The chlorine is the strong electron withdrawer, puts a lot of positive charge on that carbonyl carbon, makes it very electrophilic, whereas the nitrogen is the most electron donating, so it puts less positive charge on the carbon. You might think, oh, nitrogen's donating, why is there any positive? Well, it still has an oxygen that's withdrawing. All right, and now we've been seeing the acid, the addition elimination mechanism a lot. Let's look at a quick review of that. So general type of addition elimination mechanism. You have a nucleophile, it attacks the carbonyl, and you get your tetrahedral intermediate, and then the lone pair that was made on the oxygen drops back down during the elimination to kick out a leaving group. Many times you'll have some acid-base chemistry to set up this addition, and then you'll have acid-base chemistry to set up the elimination, but this is the overall. Here's one that a specific example where you don't have to have the acid-base, just to make a quick one. So the acid chloride is a very strong electrophile, and the hydroxide is a very strong nucleophile. This is a super favorable reaction here. So you get the addition, tetrahedral intermediate, and then chlorine's a good leaving group, doesn't need to be protonated or anything like that, so you just eliminate right away. So this one's pretty simple, huh? And if there was extra hydroxide around, it would deprotonate the carboxylic acid, of course. Oh, yeah, I did it. There it is. This is an old animation. You see I didn't have the lone pairs and stuff on there. I want you to draw on all the lone pairs on these guys. All right, here's a little more review. So we have an acid chloride, our electrophilic champ. If we add just water to this, a weak nucleophile, can it react with a strong electrophile? Of course, makes the carboxylic acid. And if you have the carboxylic acid and you add thionyl chloride, it goes back to the acid chloride. What happens when you add a weak nucleophile ethanol to the acid chloride? Makes the ester for you. And then the acid chloride, if it has just a carboxylic acid, which is a weak nucleophile as well. Did I call this an electrophile? That's a nucleophile. Weak nucleophile as well. Boom, make the anhydride. So you can see the acid chloride is a stronger electrophile than the anhydride because it can be used to make the anhydride. Okay, chapter 20, carboxylic acid derivatives. So we already looked at the different electrophilicity of carboxylic acid derivatives. And then now I'm going to talk about the temperature dependence of amides in NMR. This stuff's pretty interesting. I put this on an exam question way back when, and guess what? And then I added it to homework. Guess what? It has Yoda as well. So turns out this amide right here, methyl acetamide, it has a methyl and a hydrogen on the nitrogen. If you take the NMR of it, you see the NH is kind of a broad signal right here. You'd expect it. You might predict initially to be a 1-hydrogen singlet. And then the methyl you'd think would be a 3-hydrogen singlet, but it looks kind of like a doublet. And so when young Luke took the NMR, he was confused. And he went to his brilliant master to ask what was going on. And then Yoda, of course, said,
Young Padawan, coupling, it is not. Took the spectrum near room temperature you did. Take it again at 35 you must. Find wisdom you desire you will.
Okay, Master Yoda. So Luke went in. He was going to go to the Tashi station for some power couplers, but he decided to take the NMR again at a warmer temperature instead. So he took the NMR at 35 degrees Celsius. And when he did, this two signals here became a singlet. And this became a sharper singlet too. Interesting. So why is that? I'm going to go over to the board now and I'll show you. Okay, so that amide, pretty interesting. When we look at it, you'd expect a 3 hydrogen singlet, about 1 part, or about 2 parts per million, right? Alpha to a carbonyl. Another 3 hydrogen singlet, about 3.8 parts per million. And a 1 hydrogen singlet at about 0.5 to 5 parts per million. Like alcohols, they're all over the place. Okay, so why is this guy not a singlet when we run it at room temperature, but when we warm it up, it's then a singlet? This is what's going on. Remember how if we did our 2D NMR extra credit and I gave you this alcohol? And you determined and you found out that this methyl and this methyl were not equivalent because of the double bond. So this methyl is a 3 hydrogen doublet, and this one was a different 3 hydrogen doublet. They were very close to each other, but they weren't the same. And you could tell also because when you did the carbon NMR, you got 1, 2, 3, 4, 5 signals. These weren't equivalent. If they were, you'd only get 4. Okay, so alkenes can't rotate. That's why these methyls are different. Back to this guy now. It turns out the nitrogen is a very strong electron donor. Remember we were saying that the amides are less electrophilic than the acids, carboxylic acids and the esters, because the nitrogen is such a strong electron donor. So if it's a very strong electron donor, then that means it's influenced a lot by this resonance right here. Where it's resonating. The lone pair, the donation, the electron donation is strong into here. All right? And if that's the case, if this donation is very important, then there's a partial double bond here, but it's more than just a little bit of partial double bond. It's got a significant amount of double bond character. And if it is a double bond there, then it's like an alkene, and this methyl, when it's next to the oxygen, it's going to be different than when it's away from the oxygen. When you have this conformation. See how the methyl now is trans to the oxygen? And here the methyl is cis to the oxygen. So our idea about this is that the nitrogen is such a strong electron donor, the partial pi bond is pretty significant, and when you're near room temperature, it's like you have 2 different molecules in solution. You have it sometimes with the methyl trans, which would give you your singlet, and then very close by you have the one that's, when it's cis, would give you another singlet. I'm not sure which is more upfield or downfield, but you do see that there are 2 signals there. Then when you heat it up now, it allows this rotation to be quicker. So then the methyls are spinning like, for instance, the hydrogens on like ethanol. You know how we say that these 3 hydrogens of the methyl on the ethanol, they're all equivalent because they can spin around. Even though, now this hydrogen, if I froze it in time, it would be trans to the oxygen. This one's a little closer to the oxygen, but if it has enough rotation, it averages out. When you warm this up, you get that rotating fast enough and you get, and averages it out, so it comes to singlet. It's pretty cool. And so you see this in NMR, amides are special that way. You don't see this with esters because their donation is not as strong. So like, let's drop an ester. So if I took the NMR of this ester, I don't see that at room temperature. This looks like this is spinning enough that the methyl is just a 3 hydrogen singlet, even at room temperature. Maybe if you cooled it down, I'm not sure actually. Perhaps if you cooled it really low, if you could get your NMR to cool down, then you might be able to see that the methyl is cis and trans, but I haven't seen it. And so nitrogen is a much stronger electron donor than the oxygen. And that's important not only for our class, but also it's very important for our life on Earth, because the polypeptides in our bodies, the amino acids, when they're polymerized together, they have amide linkages. And the amide linkages, this lack of this restricted rotation, causes a lot of the three-dimensional structure of the proteins, which then affect its reactivity. You've heard a lot of these things, like the alpha helixes and the beta pleated sheets. They are largely influenced by the amide's restricted rotation. Okay, we said the acid chloride was a strong electrophile. Let's see it react with a bunch of different nucleophiles. So if we take an acid chloride like this, the 3-carbon acid chloride, and we add water to it, I believe we did that last chapter. Maybe not, actually. I don't think we did. But I'm guessing you know the answer. I actually showed you already, I think, in the intro. So here we go. You'll make the carboxylic acid. And this will be an addition elimination mechanism. I'll do some of these mechanisms for you. And then if you add an alcohol, similar to the water, it's a weak nucleophile, so it will add into there and you'll get an ester. If you add a carboxylic acid, another weak nucleophile, this is the one we did last chapter actually, and you'll get an anhydride. So you go from the strong electrophile and acid chloride to, and also another strong electrophile, but not quite as strong, a little bit milder electrophile, the anhydride like that. And then when you add an amine, that's not as weak of a nucleophile as water and alcohol, because the amine, remember, it's more of an electron donor than an oxygen, so that means it's a stronger nucleophile. It's kind of a medium strength nucleophile. This one will give you the following amide. We'll go over that mechanism. And lastly, this one, we're not going to do the mechanism, but this is interesting. Cuprates with an acid chloride, they produce ketones. Crazy, huh? So you add those 1, 2, 3 carbons of the cuprate where the chloride was. So I want you to know these overall reactions. I want you to know all the mechanisms, except for this one we won't go over, just know the overall reaction. So let's go ahead and do this. Let's do, what do you want to do? We're going to do either water or ethanol. Might as well do that. Not ethanol, I'm sorry. Isopropyl alcohol. Let's do that one. And they're going to be addition elimination mechanisms. Alright, so here we go. We have our acid chloride. It's a very strong electrophile because the chlorine is donating through resonance but withdrawing through induction, and the withdrawing is overriding the donation. So even a weak nucleophile like isopropyl alcohol is going to react with the acid chloride, and we get addition. First, you break the pi bond. You make your tetrahedral intermediate. Okay. And you might ask yourself, why not just have the nucleophile add and kick off the chlorine at the same time, like an SN2 kind of thing? The way I think of it, I think the pi bond is easier to break than that single sigma bond, even though it's carbon to chlorine. I think breaking the pi bond is easier than a sigma bond. So I like to show it breaking the pi bond, letting things rearrange and set up well to then do your elimination. So then the lone pair on the oxygen can drop back down to break the sigma bond of chloride. So that chlorine, is it a good leaving group for this? Yeah, chlorine's a weak base when it comes off, so that's a good leaving group. So you got your eliminations. It's a straight addition elimination. Got chloride over here. And your almost to your product, you've got following, and then you just got to deprotonate it. And so the chloride, it might do it occasionally, but the chloride's a pretty weak base. Most often you'll have excess alcohol around, that can deprotonate this. Whoops. Can't draw these mechanisms below once they get to my belly button. You gotta sit. Okay. So, here we go. All right, there we go. And it's a classic, just addition elimination. And now, what I would like you to do is yo this mechanism with water. Do on your own. Because the water and the alcohol, they're pretty much the same. Instead of having this isopropyl, you have another H there. It's the same thing. Good practice for you. All right, so we got those two. Let's try we'll do the amide. The amine next to make the amide. And this one we did last chapter. The key with that one, let me just point out one. I'm not going to go over this one, but I want to make sure you remember that it's the carbonyl oxygen that's going to attack, not the OH, because the carbonyl oxygen is more nucleophilic. So we have our chloride, very strong electrophile, and the amide is the amine is a kind of medium nucleophile, medium strength. It's not I wouldn't say a totally weak one. Medium nucleophile. So this reaction is going to be very fast. And so just like before, we get addition, then elimination. Addition, tetrahedral intermediate. Hopefully this is simple and you're like, why is he doing another one? I just given you more practice examples to see. So there's our tetrahedral intermediate, and then we'll eliminate. Chloride's a good leaving group, so it can pop right off right away. I got some new pens when I went in and got some lab data. It's nice to have better ink. All right, so I'm going to eliminate that chloride. Okay. All right, and then that can be deprotonated by another amine. If you didn't want to use the same amine, say this was something you made in lab and it's more valuable to you, you can use a proton sponge like we talked about before. made an amide. Okay, next up. Now let's look at an anhydride and see how it reacts. I said earlier, think of the anhydride as like a mild acid chloride, and it's pretty much the same, but you're going to get carboxylic acid as well, you'll see. So for example, if you add water to this, it's going to do an additional elimination mechanism, and you're actually just going to get the two acids back. So you just get two acids there. And you should remember that if you take acetic acid and you heat it up and you remove water, it'll make the anhydride. So it's just reversing that. Okay, so now when we add ethanol, it's a weak nucleophile, but the anhydride's a pretty strong electrophile. Not as strong as an acid chloride, but strong. So what it winds up making is carboxylic acid is like the leaving group, you could think of it, and then an ester. Like that. So think of it as like this whole side's the leaving group, and the ethanol replaced that whole thing. And hopefully you see now the ammonia will do a similar thing, but there'll be a little extra step here which you should be able to predict from your experience in lab. You'll have a carboxylic acid and an amide. I'm running out of board here, sorry. So you get your amide, but you'll use excess of this, and what will happen when you add that, it'll deprotonate it. That reaction is product favored, as you know, because the ammonium pK is about 9, whereas acetic acid's pK 4.74, about 5. Product favored. Okay, so let's look at some mechanisms for these. I'm going to do I think you could do these already, but let's go ahead and do the ammonia one. So the anhydrides, pretty strong electrophile. I'll go ahead and call it a strong electrophile. And once again, the reason being that the oxygen, say I'm going to call this as the side I'm going to react, the oxygen can donate in through resonance, withdraw through induction, but the resonance is going both ways, so it doesn't get to resonate as much in. So it's overall electron withdrawing the oxygen, so it's got a lot of positive charge there. And then when I throw in my ammonia, my Windex here, Windex is ammonia, but it's in water. Mostly water. Ammonia is a gas by itself. Alright, so this guy is a medium nucleophile. Pretty strong. Alright, so you know this is going to work out fine. We're going to get an addition. Get our tetrahedral intermediate. There we go. And then we look at this tetrahedral intermediate and we ask ourselves, is there a good leaving group on here? Yeah, the acetate is a good leaving group. It's pretty good leaving group because it's when it comes off, it's a weak base. It's not like an alkoxide. All right, so I can do the elimination right away. So I can drop this down. This nitrogen may be deprotonated before the elimination. Either way, it's fine actually. But let's do it this way. It'll be the same as the last one, you can remember. So elimination right away, and I got my acetate, which is not a bad leaving group because it's leaving groups when they come off as weak bases, they're a good leaving group. Acetate's a weak base, it's got resonance. Okay, and then more amine will come along, of course. You know what? I should have just come off as the acid. Yeah, my bad. It's comes off as the acetate, stays the acetate, because if there's amine around, it's going to be deprotonated by the amine. Yeah, so for my overall reaction, maybe I shouldn't have shown this first. I should have just said, oh yeah, we're going to get these two with that. So that's the key with mechanisms, right? You draw them out, it helps you out. And now I'm going to let you yo-yo this one, and I'll tell you what else you get. So let's see. We're going to add, eliminate, and then it's going to be the base. Yeah, that's going to be a stronger base. Yep, that's what you get. So try to yo-yo this one. Do that one on your own, and this one. Ask me if you need help. Next up, Ester Hydrolysis. Remember, hydrolysis means hydro refers to water, and to lyse is to cut. So water is going to cut the ester. How's it going to cut it? It's going to cut along through there. Actually, now that we think about it, I'm going to show you a way that one of the tools we use to confirm, not to prove, but to support a mechanism. Because you can't really prove a curved arrow mechanism, but you can disprove it, but you could support it. So let's say we're going to use O18 labeled oxygen right here. We're going to see where this oxygen ends up in the products. So oxygen, you know, is normally 16. That's the most abundant isotope. There is the O18 isotope that's less abundant, but you can make an ester with more of the O18 and then find out where it shows up in the product at the end. So what happens with this? Do we cleave across here? Do we cleave across here? What's going on? Well, when you run this experiment, you find out you'll get your carboxylic acid and the alcohol. And where will you guess the oxygen 18 ends up? It ends up on the ethanol. That means we have to have a mechanism where we break that bond right there. Okay, so here's the mechanism. It's excuse me. It's an acidic reaction, and we have a weak electrophile. The ester is weak because the oxygen is donating through resonance, withdrawing through induction, but overall it's donating, making that carbon not very positive. And then our water molecule here, our nucleophile, it's a weak nucleophile. So we got two weak things going on here. So we're going to need to use that acid, the sulfuric acid, to get things going. So yep, that's what's going to happen. This is a new reaction for you guys, but I'm hoping when I start to do it, you're going to be like, how is this new? Because we've been doing so much of this type of stuff. So here we go, let's get this. So far, I'm hoping you feel like chapter 20 here is pretty easy, and it doesn't feel unfamiliar. Okay, so we're going to first, of course, have hydronium and hydrogen sulfate because sulfuric acid is such a strong acid. And now, since our electrophile is weak and our nucleophile is weak, they won't react until we like activate one of them. Who are we going to activate? The ester. And now this ester, what is it gonna? How's it going to be protonated? Where is it more basic? On this oxygen or the double bonded oxygen? This is the O18 one. Remember, it's the carbonyl oxygen that's more basic. More basic, more nucleophilic. Because when it gets protonated, this can resonate in to support it. So, okay, we'll do that first. And how will that help us? That will help us because now, instead of having a weak electrophile, we'll have a strong electrophile. And our weak nucleophile water can add in. So it does. Oh, and remember how I was saying before? These are addition elimination mechanisms. Here's our addition. Couldn't do it right off the bat. We had to make this a strong electrophile with some protonations, proton transfers, but we got to it. Here's an addition step. Okay, and when you look at the overall product, you'll see this ethanol is the thing that has to come off. But currently, it's a bad leaving group, and this is a good leaving group. So how are we going to take care of that? Just like we've been doing all along, we're going to use a proton shuttle. In this case, the solvent, weak nucleophile, weak base water, can come over and deprotonate this. Hopefully you guys are watching this before exam 3, because this is more help with the concepts of mechanisms. Huh? Oh, I shouldn't wiggle that anymore, huh? At this point, when that oxygen gets deprotonated, now it's not a stereocenter, huh? All right, now I'm going to make the O18 a good leaving group, protonate that. I'll bring that over to the board up above. And now my O18 labeled oxygen is a good leaving group because it has a positive charge. So we are set up for what kind of step? An elimination. And in this case, it's a push-pull elimination, huh? Because the oxygen lone pair here is pushing down to make the pi bond, while the oxygen 18 is pulling electrons towards it because it has a positive charge. And this then supports our data that the O18 is on the ethanol. And finally, some water will just deprotonate that to finish off the mechanism. So these are just mechanisms that you just practice. You don't even have to spend that long on them. Just if you work out these mechanisms, it'll probably take you like 10 minutes to go through a bunch of them. If you spend a half an hour working on these mechanisms, just set a timer. You'll get so good at them that you won't need to like draw them all the way out to come up with your products overall, because you can kind of mentally see it in your head, like, Okay, I'm under acidic conditions. I'm gonna have positive charged organic intermediates. Weak and weak. Oh, make it strong. Add proton transfers. Eliminate. Bam, we're there. So, yeah, you'll get these, no problem. Now for ester hydrolysis, but this time under basic conditions. And this is a review. We've already done this. This is saponification. So we've already done saponification, but we'll review it. It's good to see it again. So before I start this mechanism, well, actually, let me do the overall first, then I'll talk about that. So why don't we do another OAT label just to get the hang of that. So last time we labeled this oxygen of the ester. Let's label the carbonyl oxygen and see what happens. So in your final product, what do you get? You get carboxylate and methanol. And where does the O18 label end up? Well, it's either here, it could be there too, because these are resonating back and forth. So it doesn't really matter. So this is equal to, I want to make sure you understand this. This equals having the O18 drawn there is the same thing, because this has resonance, so you can resonate the negative charge up to here, and you could rotate around that sigma bond. Okay, so back to what I was going to say before. Under acidic conditions, remember, we thought of positive charge, right? Organic intermediates. Now that we're under basic conditions, what are we thinking? Negative charge organic intermediates. Under acidic conditions, remember everything was weak. We had a weak electrophile, a weak nucleophile. So we had to protonate things to get it going. Under basic conditions, you have a weak electrophile again, but a strong nucleophile. So the basic mechanisms are actually shorter usually. So let's go for it. We'll start off with our, I'm going to abbreviate this guy. I'm going to write pH for phenyl. Okay, put my O18 up here. And now this is a weak electrophile. And then I'll have the hydroxide, which is a strong nucleophile. So will they react? Yes, right away they'll react. Should I protonate this first? No, because I don't have a strong acid around, and then that would make a positive charged organic intermediate, and that doesn't make sense. We're under basic conditions. So don't do that, that'll mess you up. Remember, you're under basic conditions and you have a strong nucleophile, so you just add right away. This is an additional elimination mechanism, and there we go, we added. Didn't have to do proton transfers to set up the addition, just get going. I guess the basic reaction mechanisms, they involve drivers, or maybe the acidic are they're more analytical. They take longer to get going. Here we go. And then boop. And then at this point, the O18's up here. Okay, now do we have a good leaving group? We don't have a good leaving group, but I am going to do the elimination right now. How am I going to make this leave? That means it's going to have to leave. How am I going to make it leave and it's not a good leaving group? I don't want it to come off as methoxide. Is there any tricks I can use? Yeah, the one I always like to use. I'm going to have it protonated by the water on the way off. So I'm going to drop my little pair down and then have this guy deprotonated right here. Got it. I know that's sort of funky cheating the system, but that's what we're doing. And so my O18 is over here. And my methanol was made. And another hydroxide, but we're under basic conditions. It's okay to have hydroxide around. And does the reaction stop there? No. Carboxylic acids in basic solutions are deprotonated. I was kind of disappointed, low-key disappointed when I was grading your lab exams. Yes. No, not the lab exams. The aldehyde enigma reports. Many of you are not showing your carboxylic acid deprotonated under basic conditions. So remember that. That's one of our fundamental big four reactions in lab, because when carboxylic acids are deprotonated, they become more water soluble. When they're not protonated, they're more organic soluble. And there we go. Did our O18, yeah, stayed where it should. Make water at the end. So that's the basic hydrolysis. And it's called saponification, and it's used to make soap. So I'll be remiss not to show this real quick. So here's how you make soap. This is one of the first organic chemistry reactions, maybe perhaps the first one intentionally done by humans. They didn't know the chemistry, we didn't know the chemistry that was going on, but we did it. So you take a molecule like this. What is this guy looking like? It's got a 3-carbon triol part here, what comes from the triol. That's glycerol. And then this could be long chains, right? So this is a triglyceride. 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18. 18 is the most common, huh? And then 2, 4, 6, 8, that 9? 9, 10. Sometimes you have an alkene across the 9, 10 bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then other times you can have 2, 4, 6, 8, 9. And then you can have like a polyunsaturated fat. Something like that, right? Whatever, they could all be saturated. Doesn't, just depends on what fat you're using. If you take this guy and you do basic ester hydrolysis, saponification, you add like sodium hydroxide and water. What happens? Your hydroxide adds to the esters, eliminates, and you wind up with the following. Glycerol, and the the carboxylates, fatty acids, deprotonated fatty carboxylates. 2, 4, 6, 8, 10, 12, 31, 15, 16, 17, 18, right? And then the rest of them. Okay, so why is this a soap? Oh, and let's talk a little bit more about this. This glycerol here, if I oxidize one of these, do you know what that is? If I oxidize this one, not the middle one, but if I oxidize this, but I only partially oxidize it to the aldehyde, that is glyceraldehyde. So remember, we base all our sugar nomenclature off of glyceraldehyde, which is similar to the glycerol from fats. And then when we make these carboxylates, how are they soaps? Well, what happens is if you have a grease, say grease in your shirt or on your hand, say you got some grease on your hands, it's a non-polar, long, fatty chain type of thing. You can think of it just like that. It's not very soluble in water, so if I got that grease on my hands and I go wash it just with water, it's hard for the water to remove it because the water, it's not soluble in water. Whereas if I put some soap on my hands, the fatty tails of the fatty acids can dissolve this. So the tails will stick into this. I'll just draw them like squiggly. So I'll get a bunch of tails of soap, the fats, into the grease, right? And then the carboxylate ends, they have charge to them. So you'll have what's called a micelle of negative charges on the outside, nonpolar fatty on the inside with your grease dissolved into it. And then this sphere of negative charge, water can come up, and you can see how it can hydrogen bond to it, and it could wash it away from your skin. So the water that you're washing your hands with could take it away. And there we have it, our soap. And if any of you have seen the old movie Fight Club, they were stealing fat from liposuction clinics and then turning it into soap with base, and they were selling it to people as high-end soap. They were selling their own fat back to them as soap. It's interesting. Now for amide hydrolysis, it's very similar to the ester hydrolysis. Do you think the amides are as easily hydrolyzed as the esters? Or do you think they're more, it's a little bit more difficult, like maybe you need to heat it up a little more, or add a little more stronger acid or stronger base? What's your guess? Hopefully you're guessing the amides are a little bit harder to hydrolyze because they're less electrophilic, because remember the nitrogen's such a strong electron donor. But they are hydrolyzed. For example, amide bonds are hydrolyzed when you eat protein. Your stomach's acids break down some of those bonds, and enzymes also come in there and do some of that as well. But just acid itself will break amides. All right, so let's see what happens here. What we get first is the carboxylic acid, and the amine comes off and it gets protonated because we're under acidic conditions. Oh, and then, yeah, no, that's it, perfect. And then under basic conditions, you get the carboxylate, not the carboxylic acid, because hydroxide deprotonates, and then the amine not protonated. Okay, so let's look at the mechanism. We'll do the acidic one first again. So under acidic conditions, we want strong, not strong. We want to protonate first usually, and we want positive charge organic intermediates. So here I'll be good about this. I'll show the hydronium protonating, not the hydronium, the sulfuric acid protonating the water first. This is something that's happening probably before you even add the amide, because you just have a bottle of, say, 6 molar HCl. So this has already happened. Okay, so now our amide, is that a strong nucleophile or a weak nucleophile? Not nucleophile, I'm sorry, electrophile. Is it strong or weak? This is a weak electrophile. Very weak. Even weaker than an ester. So we need to make it stronger because our nucleophile is water. That's weak too. So yeah, again, what's going to be protonated by the hydronium? Is it the nitrogen or the oxygen? Usually nitrogens are stronger bases than oxygen. Like if you compare ammonia is more basic than water. Okay. But this isn't an amine, this is an amide. So it's going to be the carbonyl again. Because this, you can see it can resonate in and help that out, right? So we're going to make this weak electrophile stronger. And now our water, which is a weak nucleophile, can react because it's a strong electrophile. So we get, like we've been saying all along, addition elimination reactions, huh? We get addition. Okay, and we don't, our best leaving group at this point is the water that just came on, and it's reversible, it comes off, but we don't want it to come off, we want that to stay on. So we have a proton transfer come along, some water, and we are under acidic conditions, we got a positive charge organic intermediate, and as I was saying, the acidic reaction conditions usually make you have a longer mechanism, huh? Because you got to do all these proton transfers to make things more reactive. There we go, no longer a stereocenter. And now what do I want to leave? I want the amine to leave. So I need to protonate it and make it a good leaving group. So the nitrogen now has a positive charge. It's got some pull to it to help it leave. And so for our elimination, it's going to be a push-pull, huh? The oxygen won't bear to push it off. Push-pull elimination. There we go. And then under these acidic conditions, this won't get deprotonated, but that still needs to be deprotonated. I can use water to deprotonate this, then protonate that, or I can just say, this can do it. Get my reaction done faster. And there we have it. We've hydrolyzed the amide. Very similar to the ester. So if you practice both of them, when you're practicing this one, you're getting better at the ester as well. Okay, now what about the basic hydrolysis? Let's do that one. This one's going to be a lot faster, you'll see. The reason being that the amide is a weak electrophile, but the hydroxide is a strong nucleophile. It's ready to go. Don't have to wait around, protonate anything to make it stronger. It can just add right in, just like we saw with the ester hydrolysis under basic conditions. And since we're under basic conditions, we want to see negative charged organic intermediates. So here we go. Okay, and now I have my tetrahedral intermediate. And do I have a good leaving group? I don't. Should I protonate the nitrogen to give it a positive charge and make it a good leaving group? I can't really do it because there's not an acid around for that. So I have to just have it come off and be protonated on the way off, the way I've been doing all along. We've been doing all along. So we're going to eliminate this way. We're going to have that amine form as it's coming off. So I'm betting some of you are like, oh, the basic mechanism is way better. Look at all this you gotta do for the acidic. And you're maybe even growing an appreciation for my weird protonate as you come off thing. So here we go, and we're almost done in just a few steps. And a lot of times students will stop at this point, but I don't want you to do that. Because if you stop at this point, that means if you're working in the lab, you're probably going to make a mistake. What I'm getting at is we're under basic conditions. We need to deprotonate this. So if you know that that's deprotonated, then you know, well, this is acetic acid. But if this was more organic, you would know, oh yeah, that's going to be in an aqueous layer. Acetic acid will be in the aqueous layer, deprotonated or not. But it's like benzoic acid if I have a phenyl here. This will be in the aqueous layer, that would be in the organic layer. So you want to make sure to show that last step. And also this last step is very product favored, so it'll help drive the reaction this way. Now to trans-esterification. This reaction, again, it's going to feel like, is this anything new? It's slightly new, but if you're thinking mechanistically, it won't feel new at all. But it's an important, good reaction, so we're going to go over it. So what happens with trans-esterification is you have an ester. It's a methyl ester, and it gets translated into ethyl ester, or whatever this happens to be. So this is a methyl ester, and it's going to be turned into an ethyl ester. So that's the trans part of the name. It's transferred into another type of ester. And why would this happen? These guys are going to be in equilibrium. The reason why it'll happen is it's a concentration thing. Let's say we start off with this at like 0.2 molar. And then our ethanol is like, I don't know, 30 molar. I gotta look that up. Let's just do that real quick. So, what's the molarity of ethanol? Just get an approximation. So, we'll look up the density and the molar mass of it. Okay, let's work this out. So, I looked up the values for ethanol. It's 0.79 grams per milliliter, so less dense than water, and 46.1 grams per mole. So let's do the calculation. So if it's 0.79 grams per milliliter of ethanol, I want to convert the grams to moles and the milliliters to liters. So I'll put 46.1 grams per mole, and then I'll turn my milliliters into liters. What's the bigger value? Liters are bigger, so I need a lot of milliliters. How many? 1,000 of them. And when you calculate this out, you get about 17 molar. So I was off. It's not 30 molar, it's like 17 molar. But still, it'll be much more concentrated than my ester. So it's like a washing away sort of thing. Like when we add D2O to an NMR tube to wash away OHs and NHs. That's what happens there. So, okay, we got the overall reaction. Let's go ahead and do the mechanism. This one, we have the ester to begin with. I'm going to do it over here. The ester, is it a strong electrophile or a weak electrophile? The ester is a weak electrophile, right? But the ethoxide is a strong nucleophile. So the strong nucleophile could react with the weak electrophile. I'm under basic conditions, so I'm looking at negative charged organic intermediate, so I can just add right away. Get a negative charged organic intermediate, get my addition. Okay, and now for my elimination, I can eliminate the methoxy and the ethoxy. And these are going back and forth. But when the methoxy comes off, it can get protonated like...
Don't!
We've been doing during our elimination. And when it gets protonated on the way off, it gives us our trans-esterification product. The mechanism is pretty quick, huh? And now what's to say the ethanol comes off instead of the methanol? It does. That's the reverse error. But why will I get overall more of this product? Because the concentration of the ethanol there'll be way more ethanols in solution, which can become ethoxides, and that's a concentration thing. So that's a transesterification. And have you seen transesterification before? You have. Remember, we did it in lab. You made fats into you took fats, but you didn't turn them into soaps. You turned it into biodiesel. So remember what you did. You took a triglyceride, like we saw for the soap synthesis. Long fatty chains on 2, 4, 6, 8, 10, 12. What is it? 2, 4, 6, 8, 10, 12, 30, 40, 50, 16, 17, 18. Usually 18 carbon chains, right? We saw some 16 as well, but most often 18. I'll just make these R's. What we did is we treated this. You allowed this to react with, this was your vegetable oil, and you allowed it to react with, I think we added, sodium hydroxide and methanol. So we made sodium methoxide. So you reacted your fat with methoxide, and what's that going to do? It's going to add tetrahedral intermediate, eliminate, and it'll eliminate the glycerol. Oh, lost the carbon. And remember, your glycerol sunk to the bottom of your separatory funnel, and then you had your methyl esters, your biodiesel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and the rest of them. So that was your biodiesel. It was transesterified. It was each ester had a methylene that was turned into a methyl. Pretty cool, right? And this is not a soap because it doesn't have the carboxylate with the negative charge that can be on the outside of the micelle. Also, some of you had problems with emulsions that formed. Emulsions are when the two layers, the glycerol and the biodiesel, didn't separate out well. And that might have been because you had some water in your reaction. If you have some water in here, then instead of getting just biodiesel, you'll get some soap, and the soap causes the emulsion to form. So you got to be careful with the amount of water that gets in there. Now for one of my favorite reactions, I don't know why, I just like this one. It is going to be a little different, not too much, but compared to the stuff we've been doing in this chapter, this is maybe the most newest reaction, or one of the newer ones. So this one's pretty cool. So if you take an organolithium or a Grignard and you add it to an ester and you add excess of it, you'll want to add excess, you will get something interesting happen. So imagine you're adding the organolithium to the carbonyl, because that's a very strong nucleophile, very strong base. And this is a weak electrophile, but a strong nucleophile is going to add. And it's not only going to add once, it's going to add twice. So you're going to get this after acidic workup. Interesting, huh? You add 1, 2. So it adds twice, and then of course you get the ethanol as well after acidic workup, like that. So let's look at the mechanism. It's a nice one. So the ester is a weak electrophile, and the organolithium is an extremely strong base and nucleophile. So weak electrophile again, very strong base nucleophile. So will it react? Yes, it'll react right away. And it adds. Are we under acidic or basic conditions? We're under extremely basic conditions. So this addition, this is an addition step, but we will see an elimination too. Let me continue on. Let's go here. We'll get a stereocenter temporarily. We've added those 2 carbons, and now it's an interesting step next, because we are not only under just basic conditions, we are under extremely basic conditions. EXTREM, basic conditions. Oh my god, I'm so bad. So under these extreme basic conditions, you can have what appears to be a terrible leaving group come off. I know I've been avoiding this by having these kind of things being eliminated with being protonated by water or an alcohol, but our reaction can't have water and alcohol at this point because it would just quench your lithium. You got diethyl non-protic solvent, non-polar. So our 2 carbons we added are still on there. And we've got this, it's a bad leaving group, but it's okay under these extreme conditions. Bad leaving group, okay here. All right, so what did we do? We went from a weak electrophile to a ketone. How does that react? Is that a weak electrophile or a strong electrophile? This is also a weak electrophile, but it's stronger than the ester. So the reason being that we saw that sp3 carbons are electron donating, but they're weak donors, where the alkoxys are electron donating and they're strong donors. They strongly activate electrophilic aromatic substitutions. They increase the rate by like 1,000-fold, whereas sp3 carbon only increases the rate by like 25. All right, so we went from a weak electrophile to still weak but stronger. So what does that mean? That means this organolithium that we have excess of is going to want to add again. And this time when it adds, it'll make a tetrahedral intermediate again, but it's not going to have a leaving group. And it's not going to be a stereocenter, so I don't want to wiggle it right now. So there's no leaving group, the reaction just stops right here. You're not going to kick off an O2 minus, you're not going to kick off an alkyl chain. So it just stops there. And then you add, part B is when you add in your hydronium. And then that is going to give you your final alcohol product, your tertiary alcohol. With this synthesis, you always wind up with a tertiary alcohol. And that will also be protonated ethoxide. That was present. We usually are focusing on this, but you can see why I drew this at the end. So pretty cool, huh? Way to make a tertiary alcohol from an ester.